In lectures 1 and 2, we covered why mammography is unique and the physics that makes it work. Now we walk into the engine room, the actual equipment. So, as we do this engineering teardown of a mammography machine, just keep that quote in mind. We're going to figure out why every single piece is designed exactly the way it is. This right here, this is our central theme for today. Dr. Jafar really nailed it. We aren't just looking at a bunch of parts. We are looking at physics that has been made tangible, made real. So, our journey through the machine begins right at the source, the highly specialized X-ray tube. This is where the photons that create our image are actually born. Okay, so the very first critical design choice is the exit window. You see, a normal X-ray tube uses a glass window. For mammography, that would be a total disaster. It would absorb pretty much all of those low-energy photons we desperately need, the 17 to 22 keV ones. That's why we use beryllium. Its atomic number is just 4, which means it's practically transparent to those crucial photons. It lets them out so they can actually do their job. Next up, let's talk focal spots. And just look at these numbers. They are tiny. Our broad spot at 0.3 millimeters is actually the same size as a fine spot in general radiography. And our own fine spot, a minuscule 0.1 millimeters. This kind of precision is absolutely essential. Why? Because we need to see microcalcifications. If the focal spot were any bigger, geometric blur would just wash them out completely. And this is just a brilliant example of turning a physics problem into a solution. The anode heel effect is usually an artifact we try to minimize. But here, we actually exploit it. We deliberately orient the tube so the cathode side, the side with a more intense X-ray beam, is aimed at the thickest part of the breast, right at the chest wall. The result? It perfectly evens out the exposure, compensating for that natural taper from the chest wall to the nipple. It's an incredibly clever piece of engineering. Okay, so we've generated our perfect X-ray beam. Now let's move on and look at the machine's structure and what is, without a doubt, the single most critical technique for getting a good mammogram. So, why 65 centimeters? This isn't some random number they pulled out of a hat. No, it's a very carefully calculated compromise. If you get any closer, geometric unsharpness for magnification starts to become a real problem. But if you get any further away, you'd have to crank up the dose and the exposure time. So, 65 centimeters. That's the sweet spot that balances all of these factors perfectly. I really can't stress this enough. If you remember only one thing about mammography technique, let it be this. Proper compression is everything. All this amazing, expensive technology we're talking about, it's all completely useless if the compression isn't done right. It is absolutely 100% non-negotiable. And here's exactly why it's so critical. There are 6, count them, 6 essential benefits. It reduces dose, it reduces scatter, it separates out overlapping tissues, it reduces geometric unsharpness, it reduces motion blur, and it creates a more uniform thickness. For your exam, the mnemonic to remember is DSSGRM. All right, time for a classic FRCR exam trap. You're going to see this one, I promise. The question is, does compression reduce the focal spot size? Take a second and think about it. The answer is a hard false. And this is so important to understand. Compression makes the image sharper, yes, but not by magically changing the X-ray tube. It works by physically bringing the breast tissue closer to the detector. It decreases the object-to-image distance, the OID. The focal spot size, that's a fixed physical property of the tube itself. Compression can't touch it. All right, so our beam has passed through the perfectly compressed breast. What happens next? Well, we've got to clean up the signal by getting rid of scatter, and then we have to capture it with incredible precision. Okay, this slide is pure gold for your exam. You absolutely have to know this distinction cold. For a standard contact view, it's simple. We use the broad 0.3 millimeter focal spot and a moving anti-scatter grid. But when we do a magnification view, the whole setup changes. We switch to that tiny 0.1 millimeter fine spot, and this is key, we get rid of the grid completely. Instead, we use an air gap to reduce scatter. So remember, magnification means fine spot, air gap, and absolutely no grid. So why did we all switch from film to digital? The answer is right here on this chart. Detective quantum efficiency, or DQE. Basically, DQE is a measure of how efficiently a detector uses X-ray dose to create a good image. And just look at that jump. Digital mammography is literally twice as efficient. That means a way better image for the same or even lower radiation dose. This one metric drove the entire digital revolution in breast imaging. You know, modern mammo machines are incredibly smart. They use a system called automatic optimization of parameters, or AOP. You can think of it like a two-stage brain. First, it sends a tiny low-dose test pulse, a little pre-exposure to check out the breast's thickness and density. Then, based on that information, it automatically picks the absolute perfect combination of settings, the target, the filter, the KV, and the MAS, to get the best possible image for that specific patient. Now let's look at the cutting edge. We're talking about the biggest advancements to happen in mammography since that switch to digital. We're talking about adding whole new dimensions to our imaging. First up is digital breast tomosynthesis, or DBT, which most people know as a 3D mammogram. The tube actually sweeps in an arc over the breast, taking a bunch of low-dose pictures from different angles. Then the computer reconstructs all of that data into a series of 1 millimeter thin slices. What's the massive advantage? It gets rid of the problem of overlapping tissue, which is why it has been a game changer for reducing callback rates and finding more cancers, especially in women with dense breasts. And then you have contrast-enhanced spectral mammography, or CESM. This is really cool. It's where mammography starts to act like functional imaging. We inject an iodine contrast agent, just like for a CT scan, and then use a special dual energy technique. The machine takes two images at different energies and subtracts them, which basically makes the normal breast tissue disappear and highlights only the areas where contrast has pooled, a potential sign of cancer. It's a really powerful problem-solving tool. And finally, we have to talk about safety and consistency. This is the bottom line. Because mammography is a screening test that we perform on millions of healthy people, the quality assurance standards are the absolute most stringent in all of radiology. There is simply no room for error. The number you have to burn into your brain is 2 milligrays. That's the maximum allowable mean glandular dose for a single view on a standard breast phantom. This isn't just a suggestion. It's a hard limit, constantly tested by medical physicists. It represents our absolute commitment to keeping the radiation dose as low as reasonably achievable. Okay, let's wrap this all up with a quick-fire review. This is your FCR cheat sheet. These are the numbers you absolutely, positively have to know. Ready? Let's go. Beryllium window, atomic number 4. Focal spots, 0.3 broad, 0.1 fine. SID, 65 centimeters, and it's fixed. Compression force, 100 to 200 newtons. Grid ratio, nice and low, 3.5 to 5 to 1. Digital pixel size, tiny, 50 to 100 microns. And finally, that all-important DQE for digital, a fantastic 55 to 65%. Got it? Good. And so we end right where we began. Every single number we just listed, every component we talked about, it's all a direct result of a physics principle, tweaked and optimized for the unique challenge of imaging the breast. The equipment really is the physics. In Lecture 4, we'll build on all this and see how these components come together to affect image quality and optimization. I'll see you there.